In the beginning of the encryption process, the plain text which is being encrypted with the Advanced Encryption Standard is first captured and then passed through the XO function with a round key as a supplement. The key expansion round keys are derived from the cipher key and then taken through the initial round, which is the initial state array, that is, the add round key segment. During the add round key segment, each byte of the state array is combined with the round key using bitwise XOR. The combined round key with the bitwise XOR is then moved to the next round, which is the sub-byte row, a non-linear substitution step where each byte is replaced with another according to a lookup table, with each byte converted to a hexadecimal value with two equal parts, with the first part being the row value and the second part being the column value. To simply put, the initial step value is passed through the substitution box and then processed to the final state array process, which is then passed on as an input to the shift row segment. It's important to note that the 16 input bytes in the substitution box are replaced by looking up in a fixed table given in a design for the generation of a matrix with 4 rows and 4 columns. The replaced byte according to the already designed lookup table is then proceeded to the next round of the process, which is the shift row segment, a transposition step where each row of the state array is shifted cyclically in a certain number of steps to the left side of the state array. In practical terms, the first row of the matrix is skipped and then shifted, as the value in the second row is shifted one place to the left, while the value in the third row is shifted but to the second place to the left, as the value in the last row, which is the fourth row, is shifted to the third place to the left. The output result of the shift process is a new set of matrix that contains the same 16 bytes as the old matrix. But in the case of the new generated matrix in the shift process, the 16 bytes have been moved in relation to each other in order to boost the complexity of the program or encryption. The output result of the shift row is then moved to the next round, which is the mixed column segment, a segment made up of mixing operation which operates on the column of the state array, made up of the combination of the 4 bytes of each column. In other words, each column of 4 bytes is replaced using a special mathematical function, which is an algorithm. This special mathematical function takes 4 bytes of a column as its input, in order to produce an output of a complete new byte made up of a new matrix of the same size of 16 bytes. It is important to note that the process taking place in the mixed column segment is not repeated in the last round of the encryption process. The generated output of the mixed column is added to the rounded key in the add round key segment, which is then combined with 4 bytes in each column. During the add round key segment, the 16 byte is treated as a 128 bit by adding a 128 bit to the OXR. But in the case of a final round, the output becomes the ciphertext. But if there is no more round to go, the output in the add round key segment becomes the input for the next round till the last round, where it becomes a ciphertext. Note that the processes involved in the mixed column segment can be repeated at a certain number of times, depending on the bit key length of the plain text being encrypted, and with each repeated step being part of each round that the encryption goes through. But during the last round of the encryption process, the mixed column segment is skipped with the rest of the remaining process remaining unchanged. Let's now take a look at a real-time encryption scenario using an advanced encryption standard. To encrypt the following plain text, which is 2192, with an advanced encryption standard encryption, the plain text, which is 2192, is first converted into a hexadecimal format, as shown on the screen. And with its encryption key being "that's my kung fu," also converted into a hexadecimal format, as displayed on the screen. Since the plain text being converted has a 128-bit key length, the process would go through 10 rounds, with the following hexadecimal being its generated keys for each round in the 10 rounds. For more detailed practical explanation and demonstration, let's take a look at the process involved in each round, using round 0 as our practical case study. During round 0, the plain text is converted into a hexadecimal key and then XOR into a new state array, which is then passed on to the next phase of the process, which is the sub-byte segment. During the substitution process in the sub-byte segment, the output from round 0 is transferred into the X box, that is, the substitution table, which is then leveraged with a completely new byte for each set of bytes, and then transferred to the shift row segment. And during the shift row segment, the value in the first row is shifted to the left by 0 place, while the value in the second row is shifted to the left by 1 place, with the value in the third row also shifted to the left by 2 places, as the value in the last row is also shifted to the left by 3 places. And in the mixed row segment, the output from the shift row segment is multiplied with a constant matrix in order to generate a new state array. The generated output from the mixed column segment, which is a new state array, is XORed with the round 1 key in round 1. And the whole process of round 0 is repeated all over again in all the 10 rounds, until the final output becomes a cipher text.